please take their seats so that we can begin with the next session on time. There's a slight change in the agenda. We'll have this session with Mr. Tanay Kulkarni first and followed by the session with Nagpur Environment Services and Revolve Inspection Technologies. I again request all the delegates to please take their seats so that we can start with the next session on time. Ruchi and Mandy, if you could assist the delegates to please. We'll have a session on showcase of noteworthy projects and best practices with Mr. Tanay Kulkarni, and I would like to invite him on the stage, Mr. Tanay Kulkarni. I'll quickly introduce Mr. Tanay Kulkarni. He is Chief Executive Officer at DTK Hydronet Solutions. He has trained several water practitioners and engineers around the globe, helping them tackle challenges using hydraulic modeling technologies. He has offered consultation to major utilities like the PUB Singapore, Colombo Municipal Corporation Sri Lanka, Department of Engineering Bhutan, Manila and Manilad Water Board Philippines, etc. In the past, he has also worked with the Bentley Systems as Water Solutions Consultant, responsible for the Asia Pacific and Middle East regions. Mr. Kulkarni is a civil engineer with a master's degree in hydraulics. He has a certification on big data from MIT, USA. We'll have his presentation first, followed by a Q&A. Mr. Kulkarni, please.
Thank you, everyone. Let me briefly explain and introduce DTK Hydronet Solutions. We are a young Indian engineering startup company founded by Devashri, Vinay and Aparna Joshi. And we are based out of Pune, India. We basically are a force of hydraulic engineers. We know nothing but hydraulics, which runs on the, in the background of water, wastewater, stormwater, floods, wherever there is a flow, right? So we understand we are hydraulic engineers. We are masters in hydraulic engineering. We have a strong expertise and rich experience in the field. We have pioneered HMAS, that is hydraulic modeling as a service in India. We provide hydraulic modeling as a service to contractors. We take responsibility to keep their hydraulic models alive. We calibrate the hydraulic models. We optimize the pumping operations. Not only that, but we also integrate the hydraulic models with their SCADA, the utilities HMI, etc. We also provide GIS consultancy, and we also master in Python and GIS customization. We provide detailed engineering designs for irrigation projects, especially piped irrigation networks and lift irrigation schemes. We also have great experience and expertise in revenue management systems. So what do? We basically provide design services. So we provide detailed hydraulic designs for your water supply schemes, underground sewerage schemes, stormwater management, lift and piped irrigation networks. We also provide solutions to improve the maintenance and performance of the network hydraulically. We provide solutions to optimize the operational behavior of the network, of the scheme. And we provide digitization services based on GIS. We also conduct GIS-based topographical aerial surveys with the use of drones and UAVs for the area of interest. When I first read about smart water, smarter planet some 10 years back, I was wondering what was it? So what makes our water utility smart? So when I first thought of it, these were the thoughts that came to me. Is it sensors, SCADA? Is it going IoT and big data? Is it predictive analytics, operational analytics? Or is it reducing NRW? Or is it all in one? So when I worked on this thought, I understood that fundamentally it only means that we want to make our systems, our schemes responsive and responsible. So becoming smart in true sense is responding when it's actually, your response is actually required at that point, and taking the responsibility, right? Not partially, but in whole. I would like to ask one question. What would you prefer? An analog phone or a smartphone? Of course, we all, use smartphones, right? So these are smart. We need to understand these are smart because these are digital, right? And going digital is the only way ahead. And we are the promoter, and we highly recommend going digital and adopting this digital life cycle. And this is our workflow and our engineering services. So when I am going to narrow down to water supply schemes, so digitization of existing assets, that is digitization of PDFs to GIS, then precise digital surveys with the use of drones, DGPS, and referencing it back to GIS. Then hydraulic modeling of water networks, analysis, design, also rehab, replacement studies on the models before actually carrying it out in the field. And then construction of assets, updating the GIS as your asset is being laid out in the field. Then connecting, this is very important, and this has not happened in South Asia. You have to connect your hydraulic models with SCADA. Now what happens is, all of us might know what hydraulic model is, but our experience and usage of hydraulic model is so limited that we only use it for design purpose, and post DPR, once the tender is awarded, we forget about hydraulic models. However, let me tell you that these hydraulic models, if kept alive, can also be wonderfully used in operations and maintenance. It can be then integrated with your SCADA so that you can take real-time actions, real-time decisions based on hydraulic intelligence, based on mathematics, on the basis of which the network was designed in first place. So this is how an aerial drone survey is conducted. And then we do ortho-mosaic imaging. We stitch all these images. So once we create an orthomosaic image, we are ready to go and digitize it. But before we digitize, we reference those images to our mean sea level with the use of differential GPS. And then we extract the terrain surface from the aerial photographs. So once this surface is extracted, you can actually create a terrain, apply some relief models, mathematical models on the terrain, and you can extract the terrain model from the surface model to gain higher precision. So here we have a master orthomosaic image. Then we have a digital terrain model. From terrain model, we are going to lay our network along the road, right? So we can extract elevations to the precision of 3rd place after decimal, 4th place after decimal, and we can create spot elevations along the road, and with the use of these spot elevations, you can create contours. And then comes digitization of the entire network, entire area. So we do topographical digitization like forest cover, water bodies, house building structures, roads, and then we can add intelligence to it, like their attributes, right? Where the locations are. We can geotag important places on the map. Then once we develop this geodatabase, we add intelligence to it by adding attributes related to water design, water network design. So if there are existing assets present in the field, you can have unique IDs, unique GIS IDs for every asset which is present. You can add metadata, like data of data to the asset, like what is the age of the pipe, who was the contractor, when was the pipe laid, right? What is the material of the pipeline, so on and so forth. Or what is the class of the pipe, what class of the valve, how much is the closure at the valve, right? And once the network is geo-referenced, this is how the geodatabase is developed. Then we create hydraulic models from this geodatabase. Now, most of us, when we say of hydraulic model, we only know of design part of hydraulic models. However, pre-execution, also you can conduct multiple tests on the hydraulic model. For example, criticality analysis. You can optimize the number of isolation valves, and you can also optimize the placement of isolation valves. Now, with the use of genetic algorithms and the algorithms that me and my team developed, you can also specifically find out the location where pressure loggers needs to be installed, the locations where flow meter needs to be installed, the critical points. And then you can, hydraulic modeling has got no limit whatsoever. You can create unlimited number of scenarios saying what will happen if the pump fails, what will happen if there is transients developed in the network, what will happen if the valve is kept kept closed, right? What will happen if I do not know the status of the valve, right? So n number of possibilities can be first modeled. See, it's a mathematical equations are being solved, right? Global gradient method for those of who know it. So global gradient methodology is used to converge it hydraulically. So here in this photo, I have taken a snapshot of the hydraulic model. See, this is how it looks. Can you count the number of scenarios that me and my team has worked on? Right? You would not find this anywhere in India. The number of scenarios that we worked was about 120, right? 30 plus 90. It was about 130 scenarios in one model. I'm not talking about n number of models and n number of EPANET files. No. It is single model with all this brilliance inside it. Then coming to the NRW part, even in the hydraulic model, you can create optimization. You can optimize the operational zones of the tank, right? Like sir mentioned previously, there was a tank which was catering demand, right? Unreasonable amount of discharge or flow was going through that tank, right? And it was hydraulically very, very unstable. So you can test the model first, and then you can propose. We can help you propose what needs to be done, where it needs to be done, right? So on and so forth. So we go for DMA demarcation for reduced NRW. So we understand the topography. As you can see, I have the contours laid on the network, and then we demarcate it on the basis of HSC, number of assessments, not on the basis of population alone. We do population density analysis so that we do not blindly say that, okay, this is the zone, X% of Ward 11 is falling in this zone, Y% of Ward 12 is falling in this zone, and hence the total population of the zone is Z. We do density analysis of the wards and of the zones so that precise allocation of demands is transferred to the hydraulic model. And then we provide dedicated feeder means to each one of these DMAs. Then we have pressure management strategies that I'm going to talk about later. We provide bulk meters. We provide DMA meters at the inlet of every DMA. Then we provide isolation valves. And this is the DMA arrangement that I'm going to talk about in my next slide. So this is how DMA 1 emerges, DMA 2 emerges, and DMA 3 emerges. So this is a typical DMA inlet that we propose in our projects. It is highly recommended with world's renowned authorities like AWWA. What they say is to have a sluice valve, and then they say that we need to have a pressure reducing valve at the inlet of every DMA. Now this might sound crazy for us if we think conventionally, but PRVs are very much required in the network. We often design the network for the next 30th year, but we fail to recognize the fact that the network is going to be constructed in the next 2 years. So the demands for the next 30 years might show you some 10 meters pressure. However, when you actually construct the network, the pressures are obviously going to be quite higher during the peak hours. And if we talk about the off-peak hours, it is going to be even larger, even higher. And all of us know, right, during the MNF, during the night flows, when there is less demand during the off-peak hours, the pressures shoot up, resulting in more distribution losses, right? So with the help of this PRV, we can actually have dynamic pressure management system inside the DMA. So as the demand decreases, it understands intelligently, and then it reduces the pressure, and thus making your network pressure dependent instead of demand driven, right? There are two different things. So this is the DMA inlet arrangement that we recommend. Step test for isolation, isolation step test for pinpointing the wider areas of the model for leakage. So all of us know what an isolation step test is. So we can actually carry it out. We can actually create operational reports for the operators to understand which valves needs to be closed when, what is the sequence of the valves, and so on and so forth. So one valve, then second, then so we are disconnecting segment by segment. We will be measuring the pressures in those segments, and then we will be able to understand which particular segment inside a DMA is leaking. Now another methodology that we adopt is the use of hydraulic model for remote leakage detection. Now this might sound a bit crazy, but this is very much possible. Now what we do inside a hydraulic model, we consider a leak as an orifice, and we calculate simple equation, flow through an orifice. Now when we calculate flow through an orifice, we all know that there is some E function, right? E variable. Now this E is coefficient of emitter, or emitter's coefficient. Now if the value of emitter coefficient is 0, then that means that there is no leak, there is no flow through that orifice. What we consider is, inside the hydraulic model, n number of junctions, we consider that all the junctions are having E equal to 0 initially. Then we go in the field and we measure all the pressure data, we collect all the flow data, and we import that data inside the model. After importing that data inside the model, we calibrate the model for E function. And all the junctions where there is a non-zero value of E, those are the leaky hotspots in the network. This has got, Bentley Systems has got patented technology, but we have got huge experience of implementing this technology with proof. So this hotspots, you all know that when I say hotspot, it's not a pinpoint in the distribution network, right? Yes, pinpointing the distribution network is quite difficult, but we get a hotspot indicating that this region is leaking. Now, what we propose is to connect your hydraulic model, to connect your SCADA sensor with the hydraulic model. All of us know what a SCADA is, right? SCADA tells me the real-time happenings at the location where a sensor is. But what about, it would be very illogical to have sensors located everywhere in my network, wouldn't it be? So what about the locations where there are no sensors? We don't know about it, right? So hydraulic model helps me with understanding that, okay, if this is the real-time situation at a given junction, then the rest of the network would behave like this. So it helps me to extrapolate this intelligence from one input to rest of the network. So these are the key projects that we have worked in the past and we are presently working on. Coimbatore, the 11 extended areas around Coimbatore, then Vellore, Erode, Tanjavur, Dindikal, Ambikapur, Rajnandgaon, and there are more than 15,000 kilometers of rural water networks where we have proposed this. Yesterday, you all saw that we won the Year in Infrastructure Award. It's like an Oscar in the field of infrastructure. We won this. We competed with China and other big names, big countries, and our startup won this prestigious award in 2018 for what we have just discussed. So why DTK? Because we have domain expertise and we are dedicated to research and innovation. We are international industry recognized organization. We provide advanced GIS analysis and digitization services. Efficiency and resilience is up to the mark. Augmentation studies and rehabilitation studies of existing water networks and leakage detection, we have solutions around that point. Hydraulic modeling and generation of reports, it's quickly done using Python scripts. And we have exhaustive MIS on every, we provide exhaustive MIS on every attribute of the water RMS. And we also have expertise around tariff analysis, demand